So, gravitation quiz. What am I going to ask you on the test about gravitation? It'll be the last part of the written section. It will have some, but not all of this. I tried to make the quiz, Roy, tougher than the test, and I'll try and drop some hints along the way as to what I feel is fair game, what I feel is, yeah, fair game, and what I feel is, no, tougher than I'm going to ask. Number one, totally fair game. Two students are sitting this far apart, so I would start out by saying, well, they want the gravitational force of attraction. Right? Now, Joel, remember, little g is the acceleration due to gravity on the Earth. That's 9.8. It's also the Earth's gravitational field strength. Big G is the number that we needed to put right here so that kilograms times kilograms divided by meters squared worked out to newtons. It was the conversion factor. That's the 6.67 times 10 to the negative 11. That's constant throughout the universe. If you're anywhere in the universe and you want to measure kilograms, and divide by meters squared and end up in newtons, that's what you multiply by. So don't get the two confused. Two students are sitting 3.5 meters apart. You know what? Let's use Stefan and Nick, 3.5 meters apart roughly, give or take. One student has a mass of 89, the other has a mass of 73. That's probably not their masses, those are a little high, but the physics here is good. What's the gravitational force? So it's going to be 6.67 times 10 to the negative 11. Mass 1, 89. Mass 2, 73. All divided by 3.5 squared. It is true that Stefan and Nick are attracted to each other. There is no denying that. However, the force of attraction, even though Valentine's Day is just around the corner, is not extraordinarily big. In fact, it's really, 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 really small. But mathematically, I'm proving right now that there is one. 6.67 times 10 to the negative 11 times 89 times 73 divided by 3.5 squared. Wow, small. 3.54 times 10 to the negative 8, is that right? Units? It's a force, newtons. Now, although I have said that Stefan and Nick are attracted to each other, because technically they are, Nick does not feel that force of attraction because just about 3.5 meters away in the other direction, which is why I picked Nick, is Doug. And Doug and Stefan have close enough to the same mass that they're both tugging in opposite directions. If you have the same force tugging in opposite directions, Nick, what's the net force overall then? 0. That's why we don't notice it. Which one do we notice? The one huge mass in our vicinity. What's the one huge mass in our vicinity? Earth. It's got a huge mass. In fact, we don't, as human beings, you don't feel the moon when it's straight above as opposed to when it's this other side of the Earth. You don't feel the difference. Although, something on Earth does. Yeah, tides, right? When the moon is right overhead, it pulls the oceans towards it. And the only way you can pull the oceans towards it, the water's got to come from somewhere. You're making the oceans slightly deeper in this area. It narrows the water on the sides of the Earth. The water sloshes back and forth, similarly to what you do with a tub. But it's a much more complicated situation because the moon is also revolving around the Earth, while the Earth is also rotating, which is why tides aren't nice round numbers. If you ever look at a tidal chart, I think it's every 12.3 hours or something like that is high tide and low tide. Oh, number 2, the force of the moon. Since it's able to move the tides, I'm expecting a bigger answer than 10 to the negative 8, like in number 1. Now, remember I told you folks that I accidentally used the wrong mass of the moon. Use that one, though, because I think on your data sheet from the gravitational forces lesson, the mass of the moon was 7 point something, something, something. I can't remember. But anyways, it's going to be 6.67 times 10 to the negative 11. First mass, Earth. Second mass, moon. Divided by distance between them, squared. I'll, for the homework and in terms of the test, I'll include them in the question somewhere or on the sheet on the front or something. Is it, do you get 4.25 times 10 to the 23rd? Is that right? Roy's nodding. I'll trust Roy. Yeah, sure, I'll trust Roy. And it's a force again, newtons. So something like anything where I simply ask you to find the gravitational force between two objects, two planets, two people, two whatever, totally fair game. In fact, that's going to be on your test for sure. First curveball, number 3. I have no problem asking you to find one mass. This one does equal masses because that's underlined and in bold. So let's write down the equation. It's gravitational force, big G, m over distance squared. Why didn't I write m1, m2? Both the same. In fact, you know what? There's a better way to write mm. Let's do that, Nick. And what are they asking me to find in this question? Mass, right? What is the mass? In other words, I'm going to get the m by itself. Now, to do that, I need to move this guy to, because I want to leave this guy here. I need to move this over. It's dividing by d squared, so how will I move it over? The opposite of dividing by d squared is what, Brad? Are you saying times d squared? You're correct. Yeah, times by d squared. I agree. How will I move the g over? What's the move of that? Times by d squared. How will I move the g over? What's it doing to the m? I'll divide, right? Always do the opposite. So it's going to go end up there, yes. End up on the bottom, yes. And I'll end up with this. Oh, but Brad, how do I get rid of a squared? Yeah, let's do that in one step. I think we can. Okay. Yep. How do I get rid of a squared? So if I've done that on the other side, the m squared would vanish because I've square rooted both sides, right? Yep, 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 yep. So the mass is going to be the force 5.83 times 10 to the negative 6. How do I know that's the force? Because they wrote newtons next to it, even though it's on the next line. I spotted the units, yes. Distance squared, 11.4 squared divided by big G. They did. Oh, I know that. That's 6.67 times 10 to the negative 11. Here we go. 5.83 scientific notation button, negative 6 times 11.4 squared divided by 6.67 scientific notation button, negative 11 equals. Double check, did I type that in right? Yes, yes, yes. Oh, square root, Mr. Duke. 3,370? Units. Kilograms. What weighs about 3,500 kilograms? Well, a couple of big trucks, like the delivery van types with the big cubes on the back or whatever, something like that.
Like the UPS trucks?
Yeah, something like a small moving van, not a big moving van, not a 5-ton.
What's the conversion of pounds? 2.2 kilograms to a pound?
Roughly. No, 2.2 pounds. Yeah, times by 2.2 to go to pounds. That's why in this number 1, when I picked both Stefan and you, that's not really accurate, because if I multiply that by 2.2, I'm sitting at like a fair chunk, about 240 pounds or something like. I don't think you guys weigh that much, but I was making up numbers. But you guys just happen to be 3.5 meters apart and have somebody else on the other side of you almost exactly the same distance to make the whole analogy of stuff canceling. Pardon me? Yeah, I totally care about your self-esteem.
Sorry, what was number 2 again?
The one that came after number 1 and before number 3.
Yes.
Okay. Number 4.
What was the answer? Oh, okay. Yep.
I thought I'd been quite clear. Calculate the gravitational force. Oh. Now that's the same equation as this one with the m1, m2, d squared. In physics 12, when we start looking at planets, we get into the habit of letting capital big M Jordan be the planet, little tiny m is the satellite or the moon or the spacecraft, and because it's orbiting in a circle, we use r for radius instead of d for distance. So I interchange the two, but I have to admit it's a habit when I start doing a planet, I use big M, little m, and a radius, because I'm just doing this same unit right now with my physics 12s, but in way more detail. Same equation though, Stefan, yes? G is, you know what, I'm going to run out of room. What word did I boldface and underline in this question? Why? Here's my question then, my friend. Am I just going to go no. And the reason is Newton's law of gravitation asks how far from the center of the planet or the object. Now, you guys are thin enough and small enough, we really never needed to take into account the fact that we should have been measuring from, if we drilled a hole right through your skull to the middle of your body, measuring right from there. You guys aren't that big. But planet makes a difference. They gave me here's the little spacecraft out there. Brad, they gave me that distance. This is 4.45 times 10 to the 5th. What I need to use is this distance, which is the orbital radius. How can I get that? Did you hear him? Add the radius of the Earth. What I need to do is really do this. Radius of the Earth plus how high above the Earth you are. That whole thing squared. More than one number on the bottom, put it in brackets. You could have Kieran added these together on a separate line and just included that in the bottom. Hey, I'm lazy, I got a good calculator, I'll try and do it in one fell swoop. Do you get 25,860? 2.59 times 10 to the 4th, is that right? That seems wrong to me. No, I think I'm right. Yeah, I'm right. So 2.59 times 10 to the 1, 2, 3, 4th. Units, newtons. By the way, for all of these, usually I go a half mark for the equation, because by the end of the year, you'll have enough equations that on your final exam, if you recognize that it's universal gravitation and you write down that equation, Joel, to me, that's worth a half mark. 1 mark for the numbers, half mark for the answer. Which means if you make a calculator mistake, but you typed everything, you did everything, but you just typed it in wrong, you can still get 1.5 out of 2. Turn the page. The gravitational force between two objects that are that far apart is, if the mass of one object is 73, what's the mass of the other object? Okay, I think I'm still going to start out with Hey, what's this question asking me to find? Mass. Let's pick. Nick, do you want to find mass 1 or mass 2? It doesn't matter, but I need to decide which one I'm going to get by itself. Mass 2? So I'm going to get this guy by itself, which means I need to move this. It's dividing times it. I need to move this. It's timesing, so. And I need to move this. It's timesing, so. Can we keep track of that in our head? I think I can. I think you're saying, if I heard you correctly, and I think I did, mass 2 is going to be the F stays, times it, divide it, divide it. Yes? Cool. Oh, and no need to square root this time or anything like that. Just plug and chug. This, I think, is fair game. The one that we did in number 3, where you had to, both masses were the same in square root, maybe as a multiple choice, nasty, but not as a written, Amanda. But if I give you, basically, as far as I'm concerned, Amanda, in this equation, there is 1, 2, 3, 4 variables, because G is always 6.67. So if I give you any 3, I expect you to be able to find the 4th. Okay? It's going to be F newtons, 5.2 times 10 to the negative 6. D, it's 4.6 times 10 to the negative 1, which is 0.46, which is less writing and typing, so I'll use that instead. Squared, divided by 6.67 times 10 to the negative 11, times mass 1, 73. Oh, that didn't work. Let's try that again. 5.2. Good gosh. Come on. Negative 6 times 0.46 squared divided by how many numbers are there in the bottom, Jordan? 2. So brackets. How many numbers on the top? Why didn't I put brackets around the top? This has to do with how your calculators are programmed. All of your calculators, I went on a rant at the beginning of the year about the importance of getting a decent calculator, yes. And one of the reasons I did that, any half-decent calculator, it's programmed that if you hit times, it'll assume it's on top. If I hadn't put a bracket here and here, when I hit times, it would have assumed that that 73 was supposed to be right there on the top. So that's why you may have noticed, Abe, I'm relaxed with the top on brackets if it's all multiplying. Now, if it's adding, I got to put it in the top in brackets no matter what. But otherwise, I can be fairly relaxed. It's the bottom I got to be paranoid about. Is the answer 226? In fact, that's probably what I started with when I made up this question. 226 units, kilograms. I would have no problem giving you the mass of both objects, the force, and saying find the distance between them. And it starts out the same way. This time we're trying to get the D by itself. This is a bit trickier because the D is on the bottom. I don't want it on the bottom. But what I can do, Brad, is I can move it up to the top over here by multiplying. You okay with that? At the same time, I can divide this guy back to here. I think I end up with this. See if you can follow it. D squared equals big G M1 M2 over F. Race, how to get rid of a squared? Right, Nick? Gone. Square root the other side. Yep, good. Let's plug and chug. D is going to be big square root of 6.67 times 10 to the negative 11. 9.9 times 10 to the third. Oh, you know what? Is each mass identical? Then I'm going to be lazy and just go like this. Times another one. That was clever. I should have noticed that sooner, though. Divided by, I need a force. Oh, there's newtons. 3.7 times 10 to the negative 5. 6.67, scientific notation button, negative 11, times 9.9, scientific notation button 3 squared, divided by 3.7. Only one number in the bottom. I can ditch the brackets. Scientific notation button, negative 5. Huh? Oh, square root, Mr. Duick. Now square root. Don't forget, square root. Do you get 13.3 meters? Is that right?
Is it just okay to assume that big G is always going to be the Earth's gravitation?
This is universal. If you happen to be on a black hole in Andromeda, I'm telling you big G is 6.67 times 10 to the negative 11. Don't get big G, which is the universal gravitational constant that goes there, confused with little g. Now this is the acceleration on the Earth. That's the one that changes depending on what planet you're on. But we don't use that in this universal gravitation equation.
Big G is always going to be that.
It's a conversion factor. It's what I need so that I can go from kilograms divided by meters squared, but end up in newtons. I need to multiply. Just like how do you go from meters per second to kilometers per hour? You times by 3.6. How do you go from kilograms divided by meters squared to newtons? You multiply by 6.67 times 10 to the negative 11, which unfortunately is a really, really small number. It was tough to find it for a while. Tough to calculate it or measure it. Number 7. Oh, speaking of other planets, let's go to Jupiter. Oh, and you notice, even without thinking about it, I went to the planetary one. Big M, little m over r squared. The force of gravity is going to be universal. Mass of Jupiter, 1.9 times 10 to the 27th, which is accurate. I looked it up. Yep. Yep. Divided by the radius of 1.43 times 10 to the 8th squared. Come on. Okay, that didn't work. Let's try this again. 6.67 times 10 to the negative 11 times 1.9 times 10 to the 27th times 90 divided by 1.43 times 10 to the 8th squared. Do you get 558? Yeah? I'm pretty sure it's 58. Isn't it 56? Okay, have I got a typo here? Well, if you answer this question, whoever's phone that was, power it off. If you answer this question properly and you don't just truncate your answer and you remember your math and physics rules, the correct answer is 558. If you, for some strange reason, feel that even though it's clearly closer to 558, you should round down for some bizarre, strange reason, then you can write 557, but I'm taking a half mark off. It's 558, boys. Let's round off properly. It is 558.
You're right.
Not if. We do. So that's fair game. I can put you on a different planet, just for fun. Gravitational field strength. This is also going to be on your test as well, but I think I give you the equation. If I don't give you the equation, there'll be a bonus question. Now, what's gravitational field strength? Well, the symbol for that is, we know it on the Earth. What's the gravitational field strength on the Earth? 9.8. Chris, how the heck can I figure out the gravitational field strength on Jupiter? We haven't been there. Nope. We're going to do it the way they did it. We said this. Nobody can argue with that. Gravity equals gravity. True? Obviously true. Then we said, okay, if you're on the Earth, you can also calculate the force of gravity by going mg. That's what we did for the first 90% of this unit, yes? But there's also a universal gravitation equation, this one. Big G, big M, little m over r squared if you're talking about a planet. Joel, my friend, what do you see right underneath my eraser right there? What do you see right underneath my eraser right there? Are you saying that the m's cancel, and lo and behold, there's the equation for calculating whatever little g is? If you plug in 6.67 times 10 to the negative 11 times the mass of the Earth divided by the radius of the Earth, you get 9.8. In fact, you get, I think it's 9.8001 or something. It's almost bang on. We want Jupiter. What was the mass of Jupiter? 1.9 times 10 to the 27 divided by 1.43. By the way, before I crunch the numbers, do you think you'll get an answer bigger or smaller than 9.8? Would Jupiter have a bigger gravitational field or a smaller gravitational field? Now, at first, I thought bigger because Jupiter has more mass. But not only does Jupiter have a bigger mass, it has a bigger radius. And the bigger number down here makes this answer smaller. So I wasn't quite sure. You know what? The fact that Jupiter is a gas giant means it's bigger than a planet of equivalent mass, if it was a rocky planet, would be. So you actually end up with a smaller gravitational field on Jupiter because its radius is so huge, because you're so far from the center of the planet. In fact, I'm going to cheat. If I bring back my previous calculation, I think it's the same, except don't I just delete the times 90? Right? Isn't that clever? 6.2. Mr. Newick, isn't that 6.1? No! It's 6.2! Round off! Always properly! It's not sig figs, it's rounding off. It's a completely different issue. Units. Meters per second squared is perfectly fine, and if you wrote that, I'll take it. Traditionally, we use meters per second squared when we're treating it as an acceleration. When we're treating it as a gravitational field strength, we call it newtons per kilogram, because acceleration, Jamie, is also force divided by mass. If F equals ma, a equals F over m. I won't take marks off if you put meters per second squared, but Doug, I'm a nerd. I'll do the correct convention, which is, if it's a gravitational field strength, call it how many newtons per kilogram is this planet pulling on us by? And then turn the page. You know what? Once again, I see above the Earth's surface. What does that mean? We're going to have to add the radius of the planet to this. This is just the same as question number 4, where they gave us the above, and we had to include the radius of the Earth. I will probably, Enzo, give you 1 on your test where you are having to include an above and include the radius of the Earth. Okay? They want the gravitational force. TJ, you going to make it? Yeah. Ah! Nothing? I missed. Shoot, I was a little to the right. You saw that? I hit Enzo right between the eyes. Gah! Aiming for TJ. Big M. Are we on the Earth? Nope. Don't use mass of the Earth. Sometimes kids get so used to that. Jupiter, which was, I can't even remember, 1.9 times 10 to the 20, 1.9 times 10 to the 27th. Second mass is 90 divided by the radius of Jupiter, 1.43 times 10 to the 8th, plus how high you are above it. Now, if instead of saying the word, Maddie, above or altitude, if I tell you it's at an orbital radius, I have already added the two together. You don't need to add the radius of the planet. Meanwhile, I think, again, I can almost use exactly the same calculation, right? I think if I go like this, I got the 6.67, I've got the 1.97. I need to insert a times 90, and I need to add a plus 7.2 times 10 to the 8th. I think I'm good. Yeah, nice. Oh, 15.3 newtons. Not a big force at all. Is the force 0? No. So will this object be slowly spiraling, falling towards Jupiter? Yeah. Oh, and the closer it gets to Jupiter, what's going to happen to that gravitational force? What if it gets twice as close? Would it be 30.6? Ah, Nick, you are on today. Did you hear him? No hesitation at all. Wouldn't it times by 4? And he said it like obvious. Duh, Mr. Duke. Yeah, it would be 60 point whatever that times by 4. In fact, if this was falling, it would be it would be not just accelerating, its acceleration would be changing. Its acceleration would be speeding up and speeding up and speeding up and speeding up. So we said that acceleration was the rate of change of velocity. So the rate of change of velocity, we call that acceleration. Does anybody know what the word is for the rate of change of acceleration? Yeah, it's a jerk. You guys all thought he was calling me that. Mr. Duick, you're going to suspend him? No, it's called a jerk. It's a good physics term. When you yank on something, what you're really doing is you're changing the rate of change of acceleration. Who came up with that? Aaron? Do you know what the rate of change of a jerk is?
No, I don't think so.
It's a snap. And the rate of change of a snap is a crackle. And the rate of change of a crackle is up. Mm-hmm. The physicists have a good sense of humor. Now, you have to have a very, very, very complicated equation and system to even end up being able to calculate those. Most things, like when you're dropping something, well, when you drop something, the acceleration is constant if we ignore air resistance. Sorry, two things. Your question? It's not an orbit. I didn't give it any sideways velocity, I don't think. It's above there, hanging there. Maybe invisible angels are holding on to it, and then they let go. Or, physics 12, this is the physics of an asteroid coming and colliding with us. Make it larger, and we actually calculate how much energy it will hit the Earth with, and it's like times 10 to the 10th or 10 to the 11th. It's big. And it happens every few million years, right? Bye-bye dinosaurs. Hello, mammals. Thank you, asteroid. You guys know today, this week, a huge asteroid just missed us, right? It passed inside certain satellites, so it was closer to us than some of our man-made satellites, and I think it was about the size of the International Space Station. Had it hit the Earth, it would have probably burned up in the atmosphere, but that detonation would have been about like a nuclear bomb going off in the atmosphere. One happened in Siberia in 1910. That's a very famous one. No one was there, but if you go to this Siberian area, all the forests for miles are flattened.
Is that the one with like the trees
Yeah.
on the side?
Yeah.
Oh,
So we know after the fact, and I think a few trappers witnessed it because there was a huge bang and hey, something happened. We saw a star and it exploded. So it happens every so often. We're due. Carpe diem. Shorter of breath, one day closer to death, right? Carpe diem sees, hey, we are one asteroid away from extinction, and we can't spot them. We don't have the technology. Unlike you think in the movies, we don't spot them until only a couple of weeks before they get in our area. And because there's all these different, what we've been looking at is the gravitational force between two objects. Understand, in real life, there's the sun, there's all the planets, they all tug. It's a very complicated system. And so our prediction of where it's going to end up, whether it's going to hit us or not, it's a probability model. And until it gets really, really, really close, we're still kind of guessing. So.
But like if an asteroid, like the size of the International Space Station,
Yep.
say it didn't burn up, or it burned up the size of that and it hit
Yep.
somewhere like in Russia or something,
Yep.
we would be affected by that?
Totally. It would throw up enough dust into the atmosphere to probably lower temperatures, which actually might be a good thing with our current climate change greenhouse gas issue. Do you guys remember about 3 years ago, Iceland had that huge volcano that was causing all of the European air flights to have to be diverted because it was spewing out so much ash? That eruption actually, I think it knocked greenhouse gases and global warming in the models down by about 0.1 degrees for that year because the ash circulated all over the planet for months. It takes a while to drift down, and it was a little shadier. We didn't notice it with our eyes, but the Earth noticed it. There was a big eruption, I think in 1880. If you Google the, I think it's called the Long Winter. There was in the 1870s or 1880s. There was 3 years in a row where spring barely got warm and summer was like spring. And crops, this is back when everybody was agriculture. Crops were not ripening the way they should be, and people were starving. And they believed that was due to a massive volcanic eruption. I think it was the Krakatoa one.
Was that in the United States where it was like a winter and spring?
No, all over the planet.
All of it. Okay, yeah.
Yeah.
Apparently there's a $1 billion, not reward, I guess, but they're going to give $1 billion to somebody who can come up with an invention to effectively take a certain amount of tons of.
Oh, we have several. The issue is there's not the political will. You're asking, can we as human beings try and do something about climate change? There's several fairly simple inventions that could be done. The issue is, first of all, we're not sure if the cure might be not worse than the disease, because when you're dealing with something as complex as the Earth, it's sort of like a big long thing of dominoes. You're not quite sure if you tip that first one if it's only going to go 4 or 5 and then stop, or if we didn't think about that, and we only got one planet. We want to be really, really careful mucking around with it. Anyways, ask me more about it later. Let's finish off this last question. And I got a couple of videos to show you, and then you got the rest of class to work. No homework for your long weekend, in theory. 2 spheres are placed so the centers are... Number 10 is, I think, tougher than I would feel comfortable asking on the test. I mean, it wants the masses. I'm going to start out once again with gravity. Oh. First mass. How could I show that the second mass was twice as big? Aaron. Sure. Yeah. Except instead of writing M2M, I want to rewrite this. Boy, my pen died there. Come on, pen. I want to rewrite this. I want to pull the 2 in front because we're used to seeing the numbers in front of things. And then I'll have a G, and I'll have MM, but what's a better way to write MM? Okay, I can do that. Cool. Now I've kind of turned it into actually very similar to question number, I think, 3 or 4, whatever it was. I want to get the M by itself. I think it was Brad who already pointed, no, it was over here somewhere. Someone pointed out times by D squared, divide by G, and divide by 2. Yeah? I'll get M squared equals the force times D squared divided by a 2 and a G. Oh, and Nick, how do I get rid of a squared? Darn right. Okay, now it's plug and chug time. The mass, mystery mass, is going to be the square root of, what did I say the force was? 2.25 times 10 to the negative 16. Not very big. I'm expecting pretty small masses. 4.9 squared divided by 2 times 6.67 times 10 to the negative 11. Uh, 2.25 yoink negative 16 times 4.9 squared divided by, oh, I got 2 things down there, a 2 and a 6.67, negative 11. What? Oh, square root now, Mr. Dewick. And you get a mass of 0.00636. You know what? You get mass 1 is 6.36 times 10 to the negative 3 kilograms. 6.36 grams. So about 6.5 paper clips. Really, Nick? Put it away. 6.5 paper clips. Oh, that's mass 1. How can I find the second mass if the second mass is twice the first one? Still have this, times 2. Mass 2 is 1.27. Isn't that 1.2, Mr. No, it's 1.27 or 1.3 times 10 to the negative 2. Good gosh, people. How many marks did I say this one was? 2 marks. I guess this one, I'm going to go 1 mark, 1 mark. Actually, this is going to end up being a bonus. Give yourself a score out of 20, but when I type this in, it's going to end up being out of 18. What'd you do?
I took half of the force actually, the Greenwich equation instead of 2 times the big G.
You took half of the force. Can you see it popping up in my equation there, right there? F over 2. Yeah, that'll get you there too. So yours is nice. That's actually a more elegant way to do it. I went more step-by-step structure. But yeah, you can see the F over 2 popping up in there. Totally. Totally fair game. Give yourself a lovely score, please, out of 20. Put your names on them. For the remainder of class, can you get out the handout that I called the Atwood Machine, this one here? Because this also has some questions, Stefan, that I think are fair game for the test. Some that are harder, and if you want to try them, you can, but I won't freak out if you can't get them. The ones that are absolutely fair game, 1, 2, 3, and 4. I'm going to give you an Atwood machine. I'm going to give you both masses, and I'm going to say find the acceleration, find the tension. In Physics 12, I'm going to give you number 5, where instead of giving you the masses, I tell you the tension and the acceleration, and I say, good, now work your way backwards and figure out what the masses have to be. It's really exactly the reverse of number 4. You still do a free body diagram, but instead of going winner minus loser equals mass of both to find A, start on the individual masses, work your way up to the double masses. Same with number 6, 7, 8, 9. 10 is a nasty scholarship one, and 11. Those are optional, but if you want to try those, I'll certainly go over those first thing on Tuesday if you have questions about them. Yeah?
Is 5 going to be on?
Did I circle it? Okay. In other words, 5, 6, 7, 8, 9, and 10, 11, those are tougher that I'm going to ask on the test. Or if I put it on there, it'll be a bonus. Like, I have no problem giving you nasties as bonuses, right? Because that's good challenges for you guys. Then, hang on a second, Jordan. After you finish that, you have the Forces Concepts Review. This is due on Thursday, and I attach the answers. Forces Unit Review, the answers are either next to each question or at the end of the exercises, depending on how fast I was typing this in. I think the answers are right. This is also due Thursday, the day of the test. When am I doing a tutorial for you guys? Wednesday? Okay. So your homework for the weekend is going to be do as much as you need to so that you're not overwhelmed next week. Or look at the study guide, look at the reviews, and if there's questions that you're going, I have no idea, hey, ask me on Tuesday during class. That would work great. Okay? Give me 1 second.